chapter. And so we're going to review tomorrow. We'll probably have to add a couple of things to our note card. And then we're going to test on Wednesday. Okay? So if those of you that were gone, you'll need to get a note card and figure out what goes on. Is that what you're asking me about? Yeah. Okay, and I am going to allow you to use that note card, so I highly recommend that you fill one out, and I will be looking at it before you use it. Okay, so we're talking about symmetry today, and you can find symmetry in all different kinds of places. And there's a couple different types we're going to talk about. The first one is reflectional symmetry. And reflectional symmetry is symmetry in which a reflection maps the figure onto itself. The line of reflection for reflectional symmetry is called the line of symmetry. So your face kind of has a line of symmetry to some extent. You draw a line down the middle of your face, one side reflects the other. You should be able, in any shape, if it's got reflectional symmetry, to draw a line and fold along that line, and everything on one side should map up to the exact same thing on the other side. Okay? So that is reflectional symmetry. Then we have rotational symmetry, and rotational symmetry occurs when you take your pre-image and you rotate it a particular angle, and the pre-image and the image are indistinguishable. So you might rotate it 60 degrees, but you can't tell. You might rotate it 180 degrees, but you can't tell that it's been rotated, okay? But it has to be less than 360 degrees, because 360 degrees takes it all the way back to where it starts, because there's 360 degrees in a circle, okay? The number of times a figure maps onto itself as it rotates from 0 to 360 is called order. So if I can rotate it 1, 2, 3 times till I get back to where I originally started, it has an order of 3. Magnitude of symmetry is the angle at which it rotates every time. Okay, and we find that by taking 360 degrees divided by the order. Okay, however many times it rotates. And that tells you what the magnitude or angle of rotation. Some books call it magnitude, and some books call it an angle of rotation. Okay, so that's the angle at which it rotates, and you can't tell that it's been changed. Okay, so we're going to identify some different types of symmetry here. What transformations can be used to map the figure onto itself? So what can we do here? Is there any kind of symmetry that we can see here? Okay, what kind? Reflectional, right? I could draw a line. Oh, it's terrible. I could draw a vertical line, and it fold it, and everything matches up perfectly, right? I could also do the same thing with a horizontal line, and it would match up perfectly. Okay, could I go diagonally? No, because if I went diagonally, like that, when I went to fold, this point of the star would be up here, okay? And this line here is shorter than this one, so it would not match up perfectly. Anything that's rectangular is not going to have diagonal reflectional symmetry, okay? Okay, what about rotational?
180 degrees.
Yeah, 180 degrees. I could take and rotate it and then rotate it again, and it would take me back to where it was. So the order would be 2, and the angle of rotation would be 180 degrees. Good. Okay, so this one has reflectional and rotational. All right. What about this one? Any reflectional symmetry on that? Okay. What? How many lines? 2. You could have 2 lines of reflection, right? I could go straight down. I could do another vertical or a horizontal. Okay. Does it have rotational? Yes. How many times could you rotate it to where it gets back? 2, right? Well, it would rotate 2 to where you get back to where you started, right? But it really just has 1 rotation as far as the change. So that one has 180 degrees rotational symmetry. All right, does this one have reflectional? Okay, how many lines? Just has 1 line of reflection. Is there any rotational? No rotational. eyes and the mouth mess that up, don't they?
How would you figure out a circle?
Well, just a plain circle, as long as there was no design, would have infinite number. You could, it would be infinite, yeah. But you would have to definitely look at the pattern on there. So if there happened to be one. Okay, this one we just want lines of symmetry. How many lines of symmetry does a regular hexagon have? Now, when it says that something is regular, that means that all the sides and all the angles are the same. Okay, I don't know if we've talked about that yet this year. Okay, so how many lines of symmetry do you think this one has? Okay, we've got one at each vertex, right? There's 3. But then I could also go right through the sides too, couldn't I? So that one has 6 lines of symmetry. What about this rectangle? Just 2. We can go here and here. Remember, with a rectangle, anything rectangularly shaped, you can't go diagonal and have reflectional symmetry. Okay, what about the trapezoid? This one would have one if it was an isosceles trapezoid. Okay, you could go straight and have one right there. But this is also a trapezoid. Okay, as long as you have one pair of parallel sides. Would that one have any lines of reflection? No. Okay, so it kind of depends on what kind of trapezoid it is. That one looks like an isosceles. Okay. Okay, so let's look at this. I'm going to... Alright, oh no, I'm not going to do that. Okay. This one, it says, for what angles of rotation does the figure map onto itself? This is an equilateral triangle. Okay, so an equilateral triangle, I could rotate it once, twice, 3 times, right? So what would be the order? No, the order would be 3, because it rotates 3 times till it gets back to where it starts. And then how would I find what the angle of rotation is, or the magnitude? It would take 360 divided by that order, okay? And so it's 120 degrees rotational symmetry. So every 120 degrees, it maps up back onto itself. Okay? What about the parallelogram? This was the one I was going to do. Okay. So here, if I put this on here, just like that, right? You can kind of rotate. That doesn't map. But then there's 1, right? And 2. Okay? So, what's the order? 2. What's the magnitude, or the angle of rotation? 180. So it's 360 divided by 2. So it's 180 degree rotational symmetry. Good. Now, there's another type of symmetry you might not have ever heard of. This is called point symmetry. And point symmetry is when, if it has 180 degree rotational symmetry, then it has point symmetry. So anytime it has 180 degree rotational symmetry, it's also going to have point symmetry. So, what are the rotational symmetries for each figure? Does it have point symmetry? So, does this one have rotational? Yes. How many times would it rotate? I think it would go 4 times, right? So if you did 360 divided by 4, that's what? 90, right? So it has 90 degree rotational symmetry, which means it also has 180 degrees, because 90 divides into 180, right? Yes. Yes. Okay, so this one also has points. Okay, what about this next one? Yes, it's going to have points also. What degree does it rotate? Just 180, right? So it has 180 degree rotational, and because of that, it also has points. Okay, here's some different shapes. Here's a flower. There's lots of symmetries in flowers and in nature and architecture. You're going to go into interior design. You need to understand about symmetry. All right. What type of symmetry does each figure have? So the flower, what kind of symmetry would it have? have rotational and reflectional. Because I could draw, you know, how many lines do you think I could draw? How many? 10? I can see 5. Where are you going to get the other 5? I think probably just 5, right? So it has 5 lines of symmetry. So it's got reflectional. Okay, what about rotational? What would be the angle of rotation, or does it have rotation? Huh? It does, right? What's the order going to be? 5. Uh-huh. So we would take 360 and divide it by 5, and so its angle of rotation, or its magnitude, is 72 degrees. Okay, what about this little game here, piece? Does it have reflectional? No, what gets in the way there? What keeps it from having, those dots keep it from having reflectional, doesn't it? Okay. What about rotational? Yes, 180. Okay, so no line, and then 180 degree rotational. Does it have point? Yes. Okay, what about a square? How many lines? It would have actually 4, wouldn't it? Because you could go vertically and horizontally, and then in a square you could go diagonally, couldn't you? Okay. All right. What would its rotational symmetry be? 90. Okay. Because 360 divided by 4, because you go 1, 2, 3, 4 back to where you started. So it'd be 90 degrees rotational. So would it have point? Rotational, I can't spell. And it has point because 90 divides into 180, right? So it's got 180 degree rotation. Okay, now this one is a little bit tricky in that the colors kind of get in the way a little bit. Okay, does it have line symmetry? Well, it's kind of hard. It's kind of hard to tell because of the angle in which it's at. It would just really depend on whether those things opened up the same. You know what I'm saying? The little flower part of it. And probably I would say no because of this flower. That kind of gets in the way too. Okay? So I do not think this one has any line symmetry. If it did, it would have to, each one of these pieces that's curved would have to open up exactly the same. And if it did, then it would. Okay? But this one to me doesn't, and this messes it up too. Okay? So we're going to say no line on this one. What about rotational? 360? You can't, well, 360 just means you can go around one time and you go back to where you begin, and so that's no rotational symmetry.
40?
Well, would you count each one of these because of the color? So it would really only go once, twice, 3, 4 times around, right? So it would be 90, okay? So it would be 90 degree rotational symmetry, and it would also have point. If I took it here to here, that's 1, and then 2, and then 3, and then 4. So it goes 4 times to where it goes back to where it starts, and then 360 divided by 4 is 90. Okay?
Would the flower affect that at all?
Yeah, I don't know about that. That's a good question. I don't know. Yeah, May would have. Yeah. Yeah, if we did it without the flower, definitely. Otherwise, yeah, it would be a little bit messed up there, wouldn't it?
So it should be no.
Well, we'll pretend like the flower's not there on this one. Okay, but probably if we were being technical, the flower would mess it up. Because it only has 5 prongs, whereas the other has 8. Right. That's interesting. Okay, you're the first person to even pop that. Okay, here's a good question. A company CEO wants a new logo that looks the same for each rotation of 30 degrees, uses the 3 company colors. What are some things that need to be considered in the design? And then we're going to talk about what would need to be considered if it was going to be 60 degrees. So you're in charge of making a design for the company, but they want your CEO wants it to be rotationally symmetrical at every 30 degrees. So what does that tell me? He's needy. Maybe he wants to make a pinwheel and put outside of his business.
There's three colors.
There's three colors.
The colors are going to be used for the product.
Four? Okay, where'd you get four from?
Because 12 times 3 is equal to 360, and then if you divide that by 3, then that equals 4.
To be a circle.
And it wouldn't be a circle, because if it rotates 30 degrees every time, it should be able to rotate 12 times, right? To where it comes back to where it started.
And then if you divide that by 3, then with the 3 colors for each color, use 4 times.
Wouldn't they be used 12 times? Because if you went 30 degrees, you'd have the same shape, 30 degrees, same shape, all the way around.
Wait, he wants the same.
He wants the same. Here, this might help you see what I'm talking about. Here's some examples. See, if you took this one has 30 degrees rotational symmetry, right? So if you took and rotated it 30 degrees, what you had here and what you had there has to be exactly the same. Okay, and then again and again and again and again and again. Okay, here's another example. This one's a little bit simpler, and this one's even more simple. Okay, now what would be true if it was 60 degrees? How many prongs would it need to have? It would need to have 6. Yeah. And when I say prongs, you know what I'm talking about? Like little points that it rotates to. The order, okay? The order of it would need to be 6. Okay? All right, so we talked about reflectional and rotational. Here's some more examples. Here's another good example of where they use several colors. Okay, this one's got 90-degree rotational symmetry, so every 90 degrees, it has to look exactly the way that it did to begin with. This one is a reflectional with the airplane. You draw the line right down the middle. You should be able to fold that airplane in half, and whatever's on it should be like it kisses. One side kisses the other, and it looks exactly the same. Okay? Here's some more pictures of some. So do you think we use symmetry in the real world? You really do. I mean, it's in nature everywhere, okay? If you're going to be an architect, you have to know a lot about symmetry, because have you ever walked into a room and it just looked like lopsided? It just was, one side was heavier than the other, okay? Or sometimes you look at a house, like some of the architecture from back in the 60s. There's this house in my aunt's neighborhood, and I swear it is the ugliest house that I've ever seen. It is just really unusually shaped, and I need to paint it because it looks terrible. But there is no symmetry to it whatsoever, and I can't hardly stand to drive by it. It's just so ugly. But anyway, so this one's got some rotational, it's got some reflectional. They really all have just a little bit of everything. So when you're out and about, look and see how much symmetry you can see out there. All right.